Thank you. I'm looking to thank you. Sorry for taking so much of your time.
So fortunately, our next speaker is my person in this room. Obviously, I think there is no further introduction. He may tell you anything you wish to tell, not only physics, but also the people. If someone would ask me what is the like, I'll need to ask them what is the like.
Yes.
All right, can go back. Yeah.
Okay, thanks.
Can you tell me where you want to start? I think it's like a 30, 35.
30 plus 30 plus 5, I think, is the plan. Can you hear me okay? Should I use the microphone? Can you hear me okay? Okay, so what I mainly plan to do actually is just to give an introduction to polariton physics, because not everybody at this meeting is an expert on polariton. So some of this will overlap with some of the ideas that Natalia introduced, but I'm going to go a little bit deeper dive into how these things actually work and some of the details. So just to start at the very beginning, can you see my mouse?
Yes. Are you on the Zoom?
I'm not seeing the mouse.
In the mouse, yeah, nice.
Hang on just a second here. It seems like it only lets you change things when you're not sharing. So let me. All right, so. All right. So now you can see that, right? So now I have to figure out how to share it. No. I can see why there was the problem there. All right. All right, now you can see my mouse, right? Okay. So polaritons. So the structure is typically a cavity, a planar cavity. And what's different from, say, a typical laser cavity is that embedded inside, we have quantum wells that typically have a very sharp excitonic resonance. And so actually, the fact that we're using excitons is not at all crucial here. What's really crucial is just that you have a sharp optical resonance, which could be a transition between any two states. In this case, it's a transition between the electron and hole states of the conduction and valence band. So in this picture then, when we have the photon in the cavity, that has a minimum in energy, which just corresponds to bouncing perpendicular between these mirrors. And then the exciton, we just write as a single energy transition independent of momentum. And so I'm going to talk about in-plane momentum. That would be for motion in the plane, where as opposed to the perpendicular bouncing between the mirrors. So when you turn on the coupling, this means that this transition can either absorb a photon or emit it. And when you turn that on, you get this coupling between the two states. And typically you write that down as a very simple matrix with Rabi coupling between the two states. And when you solve for the eigenstates, you get this type of dispersion. And the eigenstates now are going to be a superposition of some fraction of photon and some fraction of exciton. Now, uncreatively, the names of these things get called the lower polariton and the upper polariton. And we're going to focus in on this lower polariton because this here has a nice parabolic dispersion. It looks like a particle with mass. So you can ask, why did we go to the trouble of doing this? We already had photons in the cavity, so what's the mixing doing for us? Well, essentially, it makes the photons extremely interacting with each other, so that it's like, if you just think in terms of the photon picture, it's like turning up Chi3 and making these world record nonlinear optical materials. And so we have a very strong photon-photon interaction, but they also have an effective mass. And so what's going to happen then is we have particles that are approximately number conserved because they're inside of a mirror box. They have an effective mass and they repel each other. So that's going to map directly to the equations for a Bose condensate of bosonic atoms. And so just some terminology here. Typically, this is the degenerate case. It doesn't have to be perfectly degenerate. You can have the energy of the exciton and the cavity photon be different from each other. Now, here's a little bit of details that matter for a lot of the experiments, sort of zooming in on this dispersion relation. So a lot of times people will focus on this range of the spectrum, which we would typically call the polariton range, where you have an effective mass, which is very, very light. It's about 10 to the minus 3 electron masses. And all of these are easily visible to just light emission because they can turn into photons that leave the cavity. But as you can see, this is a continuous dispersion. So there's a lot of other things that are going on. So for instance, out here at very high K, there are just regular old excitons. And so if we create high in energy, we're going to typically not only create polaritons, we're going to create a bunch of excitons at high K. And so you notice there's not really a sharp boundary between these two, but we typically call them the excitons when they're up at this range. In addition, there's a region which has negative effective mass, and these tend to get called bottleneck polaritons. And so there's a transition of flow from excitons down through the bottleneck region into the polariton region. And then finally, there's also some excitons that are created that don't couple to light. And so they don't have this anti-crossing and they just stay where they were. And this is just selection rules. It's just the overall spin of the excitons. It does not match the spin of the photon. And so one of the consequences of this is that in a lot of experiments, it's either a feature or a bug, you can create a cloud of excitons just by pumping with your laser, and they will coexist with the polaritons. So you're creating the polaritons with very light mass, and then in addition, the gray and the pink populations, which are not light emitting, which are still going to be around in your population. So I'm going to focus on that first as a feature. Because they have much heavier mass than the polaritons, they tend to just stay wherever you put them. So if you have an external laser that focuses in on your planar cavity and creates a blob of these, it's going to look like a wall as seen by the polaritons. And so this has been used by numerous groups. So here's just some nice examples. This is a ring trap where the laser was focused into. Uh-oh, what happened? Did we? Oh, yeah. Unfortunately, I forget about it. It has a timer that times itself off after 2 hours. So unfortunately, we're going to have to just stall here. What I should do is turn it off during the break and then turn it on, but I have never remembered to do that. Okay, it's going to take like 3 minutes to cycle, so I'm just going to talk. Are there any questions just on basically how polaritons work while I'm stalling here? I know some of. Yeah, what about it? Okay, the reason why historically that's called a bottleneck is because if you create a bunch of excitons, you would think that, well, the polariton states are lower in energy, and so they should all just fall down into the polariton states. But the mismatch of the density of states is so large that actually the excitons have a really hard time falling down. As a matter of fact, if it wasn't for the Bose stimulation, they never would get down there. So if you are typically doing these experiments, you pump at low density, you see no polaritons to speak of, you just see a tiny bit and you see a lot of excitons. And it's only when you get stimulated scattering within the band that the excitons can even get down. And it's really just a density of states because the mass of the excitons is like 3 orders of magnitude higher than the mass of the polaritons. There's a huge density of states mismatch, and they simply can't find their way down. So that effect is already known from like the 1970s, actually going way, way back. Yeah. Yeah. So it's not completely trivial, but the the typical way people think about it is if you think of the polariton as some fraction photon and some fraction exciton, just completely ignore the photon-photon interaction, and the interaction is entirely through the excitonic part. Now, there's a whole fraught field of what's the exact polariton-polariton interaction, because the experiments typically come out much higher than what the theoretical numbers would predict they are. And that is not a fully resolved question.
On site, long range.
Pretty much view it as just, one way to think about it is you got a photon bouncing between the mirrors, and every now and then it turns into an exciton. And then if there's another exciton near it, when it did that, it's going to feel a repulsion. So it effectively leads to a short range repulsion between these things. Yeah. All right. So now I can start this up again. So again, one way to think about it, and it's interesting because the last talk that we just heard had a nonlinearity through the gain mechanism. Here, the nonlinearity is directly particle-particle interaction. It's not clear to me what completely different physics you get from those two different cases. Like in this case, we can say we can map directly to the Gross-Pitaevsky equation. In the case of a gain nonlinearity, other things are happening. You have to think about the electron hole nature separately. All right, so it's almost, oh, good. All right, that is promising. What's that? Some repairs? All right. Okay, so here's a couple experiments from a while back. One of them is, this is the laser profile. You can make a ring trap, and you can put a condensate inside of that. And in this case, you have like a drumhead mode of the condensate. And so in the place where the excitons are, that's going to be strongly scattering and repulsive of the polaritons. But in the middle, it's kind of empty. And so the polaritons can flow a lot better. This is another experiment that was done a while back in which they use it like a transistor, in which you create a bunch of polaritons here, and then you can create a blob of excitons here and block the flow of the polaritons from going down a channel. Now, another really important physics background thing to understand about the polaritons is that they're emitting light through the top mirror because there's a leakage. The mirrors are never perfect, although these are very high Q. Q typical in our samples is about 300 to 400,000. But they always emit some photons. So in a way, they can't live forever. They stay only for a while, but they can still stay long enough to thermalize and interact with each other. But that leakage photon light that's coming out is actually our data. So we can either image in real space or in Fourier space and directly see either the momentum distribution or their real space distribution. So just a little bit of detail about this. Here, this is data in which we are angle resolving, and that just directly tells us the momentum of the particles. And so we read off that dispersion relation that I showed you before. This is just directly readable in the data that we have. You can measure their dispersion relation. If you take a cut in the vertical direction, that corresponds to the spectral function. And so you can immediately learn about the occupation number. You can learn about their lifetime broadening and also coherence from line narrowing if you take a cut in this vertical direction. Now, because of this, essentially this allows us to get direct data on the occupation number as a function of K. And so this, let me remind you, because these are bosons, they're basically dressed photons, we expect to see a Bose-Einstein distribution at high density. So on a log scale, you would see a linear, Maxwell-Boltzmann is just a straight line. And then when you turn up the density, you get this peak in the ground state, which can shoot up really high. So what's nice now is that we see that exactly in data. And Hassan sitting in the room, this is his data. it used to be sort of a byword that polaritons are an intrinsically non-equilibrium system. These are perfect fits to an equilibrium Bose-Einstein distribution. And all that's really necessary, you don't have to have infinite lifetime. You just have to have the lifetime be longer than the thermalization time. And so they thermalize by collisions. And so they can do that rapidly within their lifetime. So in terms of absolute numbers, their lifetime in the cavity is a few hundred picoseconds, but the thermalization time is just a few picoseconds. And so effectively, even though these things are all on picosecond timescales, the lifetime is infinite compared to the thermalization time. And so we get really nice fits to an equilibrium Bose-Einstein distribution. Now, what can we do with this kind of condensate? Then you can see that now, this is the occupation number just shooting way up in the ground state there. All right, well, this is an older experiment, but I want to talk about this in some detail because it tells you a lot about what's going on with these things. So this is an experiment in which we have just a laser focused at one place on the sample, and it's going to give us a little exciton cloud. And at low density, that's just going to create a whole thermal cloud of polaritons, and we're going to see them flow. And so what you're looking at in this top curve is the parabola where they're created. It's just their effective mass. But then you see it's smeared to the left. And that's because there's a slope in our cavity. There's actually a wedge, which is like a gravity pulling them in one direction. So they're created in this initial parabola here with a big thermal distribution. And then they flow downhill. And at low density, they just freely flow away. And you see them running off to the left that way. All right. So that means they start, say, at zero momentum, and then they pick up negative momentum going this way. All right. Now, in this next picture, we've turned up the laser power is all we've done. And so now we have a big exciton cloud with a big potential energy. And at that point, what we see is that the population of the polaritons has gone up, and we see a sort of a narrow distribution where now there's not this big thermal distribution. And this is what we call a quasi-condensate. They're sitting on top of this hill, and they're also being pulled to the left. They're feeling they're basically freely expanding. They're not trapped. They're freely expanding and flowing off to one side. And then if we turn up the power even a little bit more, now we see a true condensate in which now you can see that this is spectrally much, much narrower than this was. Okay, so even though this was highly piled up around its ground state sitting on top of that hill, it was fairly incoherent. Whereas now this finds a little trap in this nook between the exciton cloud and the wedge, and now it's going to sit at k equals 0 as a true condensate sort of sitting right in that little trap there. So sometimes I'll talk about a true condensate, and sometimes I'll talk about a quasi-condensate. Basically, the quasi-condensate is spectrally narrow, but it's not very coherent. It's not very good for actual superfluidity and so on. And this is actually a cute experiment that we did in real space. Okay, if you look at this and think about it for a second, you'd say, okay, here is particles starting at plus k, and then they're flowing this way. So at one point they hit 0k, and then they keep going to negative and negative k. Well, in real space, that corresponds to moving uphill, turning around, and going back the other way. And this is actual time-resolved data showing the particles moving up, turning around, and going back the other way. All right, so one of the things then that is nice about these, now that you can get really nice condensates of them, is you can actually see them find their ground state. The condensate will, whatever geometry it's in, will flow to whatever its ground state is. So here's an experiment done a few years ago where this is a pillar, and because of the strains in this pillar, there's actually a minimum at the four corners. So there's this is an energy profile we mapped out, and so there's actually 4 traps. And so we're going to create in the middle of this thing, so the laser is focused at the center. And at low density, they don't really go anywhere. They just sit where the laser created them, and that's what I call the quasi-condensate. But then as you turn up the power, you notice that they find the corner. So they've flowed like 50 microns away from the creation spot, and they flow down until they fill up that. And then if we keep turning up the density, eventually they talk to each other and they phase lock into a single condensate where all four corners are now talking to each other. If we look at that in energy, it's pretty neat because what's going on, you could say, here we're looking at one of the corners, here we're looking at another one of the corners. And initially, as we turn up the density, these are two uncoupled condensates, two different energies spatially separated from each other. As we turn up the density, at some point, they actually talk to each other and phase lock and thereafter are exactly the same frequency locked to each other. And so that's going to be one of the features for these lattices. All right, so in general, when people have looked at these, you don't have to have a really complicated spatial geometry to trap them. You can just take two laser spots or four laser spots and put them near each other, and that will lead to a confining force felt by the polaritons. Sometimes you'll see something like this, which is a metastable condensate in which it's trapped, but it's not in the actual ground state of the trap. On the other hand, if the lifetime of the particles is long enough, then they can actually find the true ground state and fall down into that. And we can see both types of behavior. Now, if we make two types of trap, well, let me just say before I talk about two traps, the bottom line is that we now have something that is completely modeled by the Gross-Pidievsky equation. Several people have mentioned this already at this meeting. The sort of nominal one is this one here. If you want to account for creation and destruction of these things, leakage out and creation in, this is typically the way that's introduced, where you have a positive term and a negative term for pumping in and loss out. It turns out that in some cases, you don't need to worry about those. If the lifetime is long enough, you can just solve an equilibrium Gross-Pidievsky with no generation and no decay. Okay, so in the case where you have some kind of metastable pumping, you may have two traps. And in this case, as I showed you before, what often is going to happen is that the trapped condensate in two different traps will lock. And it's not necessarily going to be the ground state of one that locks to the other. It could be that the ground state of one is locking to a higher state in the other. But the nice thing about these laser things is that now we can control on demand the height of these as well as the spacing, and we have total control over that trap size and shape. So jumping way ahead, I just showed you two spots. Okay, this is kind of the state of the art now of groups that are doing this. This is not our data, but it looks a lot like what we just saw in the previous talk, right? You can make a whole array of polariton condensates. But what's interesting here is if you look at these spots are not where the laser is. Okay, so the laser is focusing to make this lattice, and the laser is making the barriers. And then the condensate is flowing in between the barriers. And so the bright spots that you see are not where the laser is, it's where the laser isn't. They're falling into the low energy minima between the laser spots. So in this case, the laser is generating excitons, and the excitons are creating a potential barrier in a lattice shape, and then the polaritons are flowing down into the minima in between them. Now, one of the appeals, there's a couple appeals just to think about these for just a second. One of them is just that this, you can say it's a Gross-Pidievsky equation solver, right? You create some random potential profile and you pump it, and the condensate will find the ground state of that system, and it'll do it really fast, and then you can image it in one shot and get the answer out of what you're going to see. Now, there's some other features, though, of things that are nice about polaritons. One is, as we already saw in the previous talk, because you're looking at a two-dimensional thing where you have total control over where you fire your lasers in, you can make non-trivial things like Kagome lattices, where you have missing pieces and so on. This is actually done with short lifetime polaritons more than 10 years ago by Yamamoto's group. But this is done with an actual patterning rather than with laser spots. But there's nothing to stop you from doing this with lasers as well. Another possibility is because, again, you have this two-dimensional plane. You have the case not only of having nearest neighbor interactions or everybody interacting with everybody else or all their next nearest neighbors. You could actually use external optics and take the light from one spot and just send it into one other spot and get them to talk to each other that way. And so this allows you to have very non-trivial topologies of things that are talking to each other. And probably the simplest would be like a ring in which you make one talk to somebody across the ring or something like that. Okay, so I'm not going to explain Natalia's method she already talked about this morning. But this is the polariton system that's embedded in, is what I just explained to you. So what you have in this case is these blobs are exciton clouds, and then the condensate is flowing between these, and between every two, the condensate gets trapped in like a standing wave. And that standing wave can have even or odd number of nodes. And so then that gets to be counted like a bit. You can call it, so it's interesting because when you think about atomic lattices, you're thinking of one atom per lattice site. Here you're talking about something that's a wave, basically, but that wave has a binary nature to it and being able to have either even or odd number of nodes sitting in there. And so Natalia worked out how to map this over to the XY model. But in principle, you can make the height of each of these different using an SLM. And so encode very non-trivial information into this potential energy profile in order to solve a non-trivial problem. And so you can see here just, if I take a straight line between any of these two, I can see either an even or an odd number of nodes along that path. Okay, so I want to spend just a little time thinking about how good could this be? So there's two questions one can ask. One is, I basically said you in the experiments, you make the condensate and just bang, it finds the ground state. It's really quite dramatic in the experiments because you turn up this knob and suddenly it pops into its ground state of the whole system. How long does that actually take? And then another question is like, what's the scalability? How far can we scale these? And when we had the precursor to this meeting several years ago, we spent some time debating about that because there are theorems involved. Okay, so the first one is actually pretty straightforward. If I make a condensate and that condensate has phase noise, the amount of time that it takes for it to get a common phase coherence is basically however long it takes a sound wave to propagate from one side of the system to the other. And so that's going to scale with the size of the system. And so if we have a two-dimensional grid, that's going to scale as the square root of n. So that's actually a pretty decent scaling. That's not something that's going to really cause huge problems. And this is done in 3 dimensions by Natasha in a previous life many years ago. And it's actually a really hotly debated question for several years as to how long does it actually take for a condensate to find a common phase. And I think there's pretty much a consensus. It scales with how long does it take for a sound wave to get from one side to the other. On the other hand, the spatial size, how big of a condensate can you make? In 2 dimensions, there's a theorem, the Berezinski-Kostelis-Thouless theorem, it basically says you cannot have infinite long-range order. And so this is a very nice model done by Hassan of just solving Gross-Pidievsky and then plotting the correlation function, the first-order correlation, as you turn up the density. And what you see is below a certain density, you have exponential decay of the correlation function. So that would be really no long-range order. And then at high density, you see a power law decay, and that's perfectly consistent with the Kostelis-Thouless prediction that decays as r to the negative 1/4. So it's slower than exponential, but it's not infinite range. It doesn't go on forever. And of course, then there's a critical density at which you go from a second derivative down to a second derivative up, and that would be your superfluid transition density in all of this. Interestingly, all of this is solved without any dissipation or anything like this. It's just standard 2D condensate physics. So the theorem would say you cannot scale to infinity. You can't make n nodes. And it's actually a question I think that implies that's also true for a lattice, right? So this is the theory for a homogeneous 2D Bose condensate, but it's probably also true that if you have a two-dimensional lattice, you cannot have this one here be coherent with this one infinitely far away. At some point, they will become out of phase with each other. But I've never actually seen that proven rigorously. It just seems to make sense. On the other hand, when you say it can't be infinite range, that doesn't mean that you can't have a pretty large range. And so, in fact, in all these polariton condensates, they're all two-dimensional. So in principle, none of them has infinite range coherence. But you actually can have the coherence length be much, much larger than the actual size of the system in realistic systems. And so we can measure that. The typical way you do that is you take an image of the light emission, you send it through Michelson, you flip one of the images, and you interfere it with itself. And when you do that, you get very nice data showing, when you're not a condensate, you just have pretty much an incoherent background. And as you turn up the condensate, you get really nice fringes. And without going into detail, you can then use this type of data to extract the coherent fraction. So you can look at, say, here's the visibility, a certain fraction of it is coherent, a certain fraction is incoherent. And then you can compare that to theories. So this is data just from the last year. This is really beautiful in so many ways. The red circles are data from our 2D experiments, and the blue line is a theory for a homogeneous thermal two-dimensional gas. There's no fit parameters. All right. It's entirely just based on the temperature of the gas and the density, which of course then the mass of the particles will set that effective. What's the units for density, basically in terms of the wavelength of the particles. So you learn a lot of things from this. One of them is that the superfluid transition is right about here. The coherent fraction doesn't show anything sharp happening. You just see the coherent fraction increasing continuously. But down here, you would say the correlation function of the coherence is going to be exponentially decaying, whereas above this threshold, you're going to have long-range coherence. But the other thing you can see is actually this curve here will go up to near 100%. And so in real experiments, we can see the whole thing is just completely coherent all the way across. All right, how much time? I think I have maybe like 5 minutes or less left. Okay, yeah, because I got a little bit of a late start. So just with the last couple minutes, I just want to throw this out. It's long been a byword with these polaritons that the gallium arsenide results, everything I've shown you is with gallium arsenide quantum wells. And the byword is that they only work at low temperature. And if you want to do room temperature polaritons, you have to have a special material, like a 2D material or an organic or perovskite or something like that. It turns out if you just redesign the gallium arsenide slightly, you get perfectly good strong coupling at room temperature. And kind of kicking ourselves because this is an experiment we could have done 5 to 10 years ago, but we didn't think to do, which is simply to redesign the cavity to reflect where the exciton is at room temperature rather than at low temperature. And so here you can see anti-crossing. In this case, the anti-crossing is not at k equals 0. It's at a higher k value. But this is, again, the upper polariton and the lower polariton with an anti-crossing. And also, what's very comforting for us is that we no longer have to have the magic sample from Lauren Pfeiffer, the only person in the world, but actually there's another group, Zbigniew Zalewski at Waterloo, that's making samples nearly as good, showing very similar results. And so the method of making these is now broken out from Lauren Pfeiffer's labs. This is just a fit. This is detuning. You can see here going from excitonic to photonic. And this is theory on this side, and this is the experimental data on the other side. Again, I said one way to think about these things is simply view them as very nonlinear photons. And so if you don't even worry about polaritons, you can just look at this. This is, again, room temperature data. You can see that there's a very strong shift of the line. Here's the low density data. Here's the high density data where it's a condensate. And that's shifting like 10 millivolts or more. And we see that, and this is now plotting the upper and lower polariton energies as a function of the, I didn't put the axis here, this is power, log power. And you can see you get, a multi-millivolt shift of the lines, which means this becomes, totally apart from condensate physics, it just becomes a good nonlinear optical object. So we're very excited about these room temperature results, and we're continuing to push on that. So I think I can finish then. So again, one of the take-home messages is that the polariton condensate will optimize. It's already been mentioned that it's going to find the ground state of whatever complicated potential you have. And you can actually design it on purpose to have gain and dissipation be important, in which case you have a metastable state. And that will also find that very rapidly because, again, the stimulated scattering of bosons makes it find one common state very, very fast. Now, in all the experiments I showed you, we were using an exciton cloud to make the potential energy profile. The advantage of that is that you can tailor your potential energy profile almost anything you want to make it as high, as wide as you want. On the other hand, it does mean you're taking part of your laser power to making the potential energy profile. And so you run out of power if you want to make lots of condensates. And so an alternative method, which I didn't talk about, is to use electric field to trap or to shift these things. And that works very well, but a problem is turning on and off electric fields is just intrinsically slower and typically nanoseconds rather than picoseconds. And finally, I just shared recent data that it's room temperature operation is realistic in gallium arsenide, not just in special exotic materials. Let me thank my group here. And if you go on the excursion this afternoon, you'll see some of these nice waterfall areas here. All right, so I'll finish with that. Thanks.
I think we can still do one question. Yes?
Yeah, we have.
For the next stable for long range traffic, you can go out to zero and come back.
Yeah.
Zero is like 99.999. How easy is it to go out and then come back? You have to match the phase and everything has to be like extremely sensitive. Did anyone show that?
Like I said, this is an ongoing experiment even as we speak. Yeah. So the answer is yes, you can get the light to come back, but you have a lot of losses along the way. And so actually part of the trick seems to be to not use the highest Q cavity, to use a lower Q cavity so that you actually get more light out and it's easier to get the light back in again. Yeah, it's like literally in the past month has been what we've been working on with this. We have a way of doing it now that we have these newly designed cavities, but I don't have any good data to show yet.
I was very again intrigued about gallium arsenide and temperature. So can you say what is the difference with gallium arsenide samples at cryogenic temperatures? You mentioned stronger nonlinearity, but in terms of more photonic or more excitonic, because once you have more photonic, it means that you can couple larger range.
So yeah, so the detuning you can do at room temperature, just the same range. You can go excitonic, photonic, or whatever. The biggest difference, I think, is that at room temperature, you have coexistence with free electrons and holes. So at low temperature, pretty much the polaritons are low in energy compared to everything else. And so you may have some free electrons around, but they are sort of, mostly going to fall eventually down into these polariton states. If you look at this data here, you can see we're getting lots of emission from up here in the upper branch, and that's thermal equilibrium, right, at room temperature. So the theory fits here are fitting it to a temperature, which is an equilibrium temperature. What that does is because you have those lots of other things floating around, then it broadens the lines. Okay, so you are mixing a photon, which is a very narrow line, with an exciton, which is broader than it would be at low temperature. All right, and so that was assumed to be a killer, and it would not work at all. And it turns out, well, it's a slight killer. Like it degrades the quality, but it does not kill it absolutely. Well, okay, so this is partly a materials thing. Almost every other material system that we've worked with, either at room temperature, either dies after a few experiments, or it's full of disorder or full of strain. And like just reproducible good samples at room temperature, if you're working with 2D or organic materials, it's just like your samples are constantly dying on you. Gallium arsenide sits there forever. Okay, for sake of time, we should probably end. Okay, well, thank you.